Let's talk about programmable RGB LEDs, otherwise known as pixels. Pixels come in two primary types: dumb pixels that require a control signal for each of the colors, and the strip has the same color across it. Useful in some cases. Smart pixels allows for the control of each individual LED and its colors. You can have one blue, the next one red, one flashing, one solid, and so on. These types are generally known as the WS2811, WS2812, and 12B. The timing protocol is rather specific as expected. You need something like a microcontroller that can generate those control signals. A few years ago, a small single-board computer arrived, or rather exploded on the scene, and it cost around $35, called the Raspberry Pi. Its low cost and general availability put it in the hands of hobbyists and developers. It runs as a Linux operating system and gives us lots of general-purpose I/O. It also gives us, on the 2B and the 3B versions, 2 PWM or pulse width modulation outputs. That's important because remember, the pixels require specific timing or else they may not operate as expected. A lot of people thought, hey, this might give us a low-cost method of driving the pixels rather than using a full-blown computer. But the timing was an issue, so one day a very brilliant engineer, Garf, who I have the pleasure of working with, coded up a method of using the PWM outputs, plus some other clever coding tricks, and allowed the Pi to drive the pixels and on two different channels nonetheless. Now, the thing is, the pixel controls are 5 volts. The Pi puts out 3.3 volt signals. Some have been able to drive the pixels directly, but it may not work each time. There's the issue of physics and thresholds and such, but we won't get into that. What you really need is convert the Pi's 3.3 volts to 5 volts. What about driving over long distance? You may not want the Pi sitting where your pixels are mounted. So the Pixel Pi board. It plugs right into the Pi. As you can see, there's a number of different connectors, so let's talk about what we have here. First of all, power. Well, the Pi gets its own power from this connector right here. And that's fine. We plug in just a standard USB cable under there that they suggest. The 5 volts for the Pixel Pi board comes in two different places. You can have a barrel jack right here from the standard power supply that a lot of people are used to, or this 2-pin removable header. This is what I prefer for a lot of projects because it gives you the ability to plug and unplug high current power supplies. The incoming 5 volts is protected on the board by a resettable fuse. This USB jack here is to drive 5 volts out to another device, perhaps the Pi. Across the bottom we have RJ45 jacks. Now you're thinking we have 4 jacks, but we only have 2 channels of output. Well, we split them into channel 1 and channel 2. Each of the outputs is split again, so we actually have 2 identical strings coming off here, 2 off here, again 2 and 2. Well, that's great, but what do we do at the other end of that? And we use Cat5 because Cat5 Ethernet cable is cheap and plentiful. You can get it from a number of sources. You get it pre-terminated. You don't have to worry about crimping your own connectors on there. Just a good cable to use. On the other side here, we have 2 other connectors. And those connectors are used to be able to drive out pixels directly from this board, pixel strings. That's kind of used as a test, but nothing says you don't have to have your strings 20, 30, 40, 50 feet from your controller board. Gives you the options. Also because maybe you don't want to drive this with a Pi. Maybe you're interested in driving it with your Arduino or a PIC microcontroller. We have 3.3 volt regulator on board here, not populated in this case, that will allow you to bring the 5 volts in, give you 3.3 volts on the output of this connector to where you can drive another device and connect it in. Gives us options. So, what do we do at the other end of these cables? We got to cut off the end and strip off the wires? No. That brings us to the endpoint. This is an endpoint. So you can see that the Cat5 cable plugs one side, power comes in, and a pixel strip is connected. So here we have the Pixel Pi
plugged into the Raspberry Pi, and you can see the blue LED on, indicating that we have power. By the way, that LED is after the fuse, so if you have no LED, it means you probably got a short somewhere and that fuse is blown. It will reset itself, given a little bit of time. We have Ethernet cables plugged in. We've got a short 3-foot piece. We've got a 50-foot length. We have a 75-foot length, and we have a 100-foot length. Simply just to demonstrate the fact that we can drive over long distances. Now remember, Jer Garf had written that underlying code to run on the Pi to drive out pixels directly. Well, some guys created this Falcon player, and it runs on the Pi directly. It brings up this nice web page, and it uses that underlying code that Jer wrote in order to drive out these WS28XX pixel strings. It does a number of other type of pixel strings as well on different interfaces, but I'm using this to just show a demonstration because it's a nice piece of software, very well written. If you're planning on using the Pi with this, you may want to take a look at this piece of software, Falcon Player. So the Pi is networked to my laptop. Simply go into Input-Output Setup, Channel Outputs, Other, and it will tell you bring up other outputs. You can add, and it's the RPI WS281X. In the output setup, you set up for string number 1 and string number 2. You can set up the order and the number of pixels and the number of channels. Remember, each pixel is actually 3 channels: the red, the green, the blue. So I'm setting up string number 1 for 10 pixels and string number 2 for 15 pixels, simply to demonstrate the fact that we have 2 different strings running on here from 2 different control outputs. You go over to Status Control, Display Testing, and you can enable the test mode. There's other things in there to set up: start channel, end channel, patterns, things like that. We'll leave that alone for right now. We'll just enable test mode. Hey, look at that. We have 10 pixels and 15 pixels running from the 2 different channels. Now remember, each pixel will redrive the output. And so the only pixel you have to worry about driving is that first pixel. Once you get to the first pixel, the second one's driven by the first, so on and so forth. So this is showing that you can drive over 100 feet of Cat5 to an endpoint without any problems. It's actually the very bottom string that's being driven by 100 feet. And if there was a problem, it would be very evident. It would show up. But the 2 strings are in sync. Actually, all 4 strings are in sync. And that's just the fact of this test mode, that it doesn't put out different patterns for each one, but it will control each one independently, as shown. One thing you may want to notice is that each one of these endpoints does have the 2 identical outputs, and I've just wired them up alternately to show that yes, indeed, they're both all being driven. And take note that it's not a split divider. These were individual drivers from the control board there. So this test pattern, you can do quite a few different things. You can change them. You can change the refresh rate. Make it very slow. So that's it for the demonstration of the Pixel Pi board. Hope that you enjoyed it and that you will support me on Kickstarter. Thank you.